I've been in this business for a long time, and I think there's some really interesting things that have been happening lately that have kind of started to motivate us to what's being called modernization, or digitizing our business. And just really quick, I don't want to spend too much time on this, but really quick, it kind of falls into a bunch of different areas, but these are some of the top ones that I keep seeing. The customers want a lot from our systems. They want systems that work. They never go down. They have really, really fast response times. I have a wife and daughter whose patience for a bad system are like this big. So my wife and daughter, if they run into an app that doesn't work well, they're gone. They're just gone, and they won't come back to an app. And no big surprise, the business wants to move fast as well. But I grew up in an era where, like 6-month release cycles. And even back, say 10, 15 years ago, I couldn't imagine that the business would tolerate these kinds of things, but they did. We didn't have any choice. But I think the bigger one that's happening is that the amount of data that we're going to be processing, or many of you are probably already processing, is just going to skyrocket. And that's really going to change some of the characteristics of the systems that we build. So in a way, I think we're in the middle of this renaissance in the way we architect systems. For many, I think they look at it as painful, but like in the talk that you did yesterday, I think that some of these new ways of building systems are really, really interesting. And they open up tons of opportunities that we're just starting to become aware of. So I think it's a really excellent time to be in this business right now. And all these discussions usually start with the monolith. How many recognize what this picture's from?
What is it? 2001?
A fair amount, yeah, 2001. It's going to be 50 next year. I can't believe it. 50 years old next year. It's an amazing movie. Anyways, the monolith. The way I kind of look at the monolith, I like to look at the monolith, is just not code, it's data as well. And as I'll go through, a lot of the challenges that people are running into with modernizing monoliths is it's relatively easy to start to modernize the code. It's typically harder, especially in big enterprise spaces, to modernize the data. Like break apart the database. That one's a big one. You may have heard this term about monoliths, this big ball of mud. I'm not here to beat up the monolith. The monolith, many of us know and love them. We know how to build them. The technology is really well oiled. We know what we're doing with these things. So I'm not here to say, oh yeah, you have to go screaming away from monoliths. And I don't necessarily like this terminology used against the monolith. The monolith has a place. But in some cases, when you have really big monoliths with really big teams, and they're hard to maintain, those are the classic big balls of mud. But monoliths, we know how to build them. We know how to scale them. We know how to make them work. And they've served us well for a long time, and they're going to continue to serve us well. But the challenge has been, for a long time, that we're always playing this balancing game. And it's not just with like the hardware capacity, but it's the architectural limitations of the systems as well. In that, you've got this situation where you're trying to have just enough scale so that you're not spending too much money on the infrastructure to run your application, but you handle those peaks and valleys. I was at Hewlett-Packard forever, and I was in IT for the last part of my time at HP, and we had tens of thousands of servers in HP, on-premise. And one of the things that drove my management nuts was overall, our utilization of those servers was around 10%. Drove them absolutely crazy because we're spending all this money on all this beautiful hardware and we're only using 10% of it. And part of the reason is that you have to scale for the peaks. And the problem is, and yesterday is the classic day where systems run into Black Friday, where systems run into this. Right, where you don't have enough capacity to handle that big spike, that big seasonal spike. And it's not necessarily that you can throw more hardware at these things as well. And this is part of the point I want to make in this talk, is that there's limitations at an architectural level that hold you back. It's like, how much parallelization can you get out of your system? And if you can't get enough parallelization, you're going to run out of capacity no matter how much hardware you throw at a problem. So there's things like points of contention. And I'm going to pick on the database, because that's the thing that used to cause me the most grief in my career, is you build a system and everything's working great, and you start to run into performance issues, and typically the performance issues, not all the time, but more often than not, would be at the database level. You just couldn't push the database any faster. And I had the ones that were really nasty, and we knew we were stuck, and there was nothing we could do about it. We were stuck on that database, and all the experts came out and tried to fix it, but they just couldn't, we couldn't make it go any faster. But there's also, even though many databases, I'm talking about traditional like relational databases, many databases are hardened pretty well, they still go down. So you still have single points of failure, which is another thing that drove us nuts. Where you have a system that goes offline, and maybe goes offline for half a day or something, and people are just panicking. So there's this real, in many cases, this is push to modernize the monolith. And this is a big part of what we do at Lightbend. We're trying to enable companies with the technologies to do these kinds of things. But how do you do it? What's the approach? So if you're in a situation where you've got a monolith, one of the approaches that many people are starting to take, and it's my job, it's really fun because I get to talk to so many different people and hear what they're doing. And part of the picture that's starting to emerge for me is that some people are starting to chip away at the monolith. They'll take some code and they'll chip a little bit away, and they're taking some of the functionality out of the monolith, and they're putting it into microservices. And if you've listened to any talks by Jonas Bonaire, who's one of the co-founders of Lightbend, he calls them microlists, or distributed monoliths. And because what's happened here is that we've broken out the code, which is a step in the right direction, but we haven't broken out the data. And I've talked to a lot of people that are doing this. I don't know how, those of you that are doing microservices, if you're cracking this nut. I know, like, again, back at HP, data was sacred. We had data architects, we had database teams, and I'm trying to imagine me going back to that environment and saying, oh, I want to break up the database, so each microservice has its own data. And I think they would have just tarred and feathered me and thrown me out of the building. But the challenge is, though, even though this is a step in the right direction, where you're starting to break apart the code, you still got a situation where you have some of those problems or potential problems that maybe you're not going to be able to hit those spikes because you still got contention at the database level, and you still got single points of failure. So the goal really with these approaches, one of the fundamental goals is, I really like this terminology, strong cohesion on the inside and low coupling on the outside, or loose coupling on the outside. And what this means is that when you're starting to distribute a system across, say, microservices or something like that, you're trying to break apart a system, you want as loose as possible coupling between microservices. And it doesn't matter, this is a technology thing, it's not a team thing, I think, because in many cases, you have a relatively small team, and you're all working on a group of microservices instead of one big monolith. So it's not like I'm working on one microservice and you're working on another one. We're all probably working on the same stuff. This is more of an architectural thing that we want to loosely couple our microservices. And a way to do that, like what we heard yesterday, is things like event-driven, domain-driven design approaches, things like that, because that gives you that strong cohesion. You only put inside a microservice what really needs to be there, but don't kitchen sink it. So these are three general goals that questions I usually ask people when they say they're doing microservices, and you're trying to build a system of loosely coupled services. So the first goal is, what you're building, is it independently deployable? And that's usually the easy one. If you can make a microlith, a distributed monolith, and have independently deployable units. The second one is harder. This is where you're starting to break apart the database. And does the service own its own schema? And that one, I've relatively few people that I've run to do this. It's getting better all the time, but relatively few. And then the final one is, the only way to get to the data that is owned by a microservice is through its API. And we're going to talk quite a bit about this one. And to give you an idea of how important some people consider this to be. This is a mandate that came out at Amazon back in 2002. And it basically is saying that from this point forward, the only way you're going to get to services is through the interface, through the API. No cheating, no backdoors, none at all. And if you don't do it, you're fired. That was Jeff Bezos back in 2002. And that's how seriously they take it at Amazon. So the idea is that, part of the idea is that you start to be able to build a system where part of the system can take a hit, but the overall system itself keeps running. And there's things like, there's a classic Netflix example, like with Netflix, when you go to a device, when a device talks to Netflix, it's talking to a whole bunch of backend services, and they're all providing information that comes back to the interface. If one of those services happens to be down, like movie recommendations based on the user, there'll be a default. So there'll still be movie recommendations that you'll see as a user, but it won't be customized for you. So and it could be just momentary while, say, this service is down for a little bit. But while that's going on, there's some compensating actions that occur. The system itself is still up from the perspective of the users, which is a really strong capability. But I think where things get really cool, and this is where I'm going to get into, is the interesting dynamics that seems to occur in some microservice systems is when you start to do things where the services themselves are interacting with each other. So it's really not this nice, clean matrix of services where all these services are just independent, but they don't talk to each other. In many cases, you have a situation where you've got services communicating with each other. And that's where I think things get really fun. So as an example, there was this really good series of articles written, I think it was earlier this year or last year, by Chris Richardson. And it was called Developing Transactional Microservices Using Aggregates, Events, Sourcing, and CQRS. And it was part 1 and 2. Really good articles to read through. And one of the scenarios that he walked through was the exchange of interactions between two services. In this case, it was a customer service and an order service. And I want to walk you through this, give you an idea of what's going on. So we had this customer service and this order service. So the order service is taking the order. So say a create order happens. And so now an order created event is emitted, right? So this is a transaction that occurred. It's done. It's in the past. It's happened, right? After that transaction occurs, some form of a message is sent from, and I'm not going to get into the exact way it's done, but it's some form of a message is sent from the order service to the customer service, saying that, hey, it's an event. Order has been created, right? The customer service gets it, and it does another transaction. What it does is it checks the credit of the customer. And if the customer has sufficient credit, it reserves the credit for the customer. So now a second transaction occurred. And then now there's a response, or some return message going back from customer back to order saying, credit has been reserved. And then this finally triggers a third transaction of order approved. So the state of the order changes from a new order to an approved order. Right? But it doesn't happen until the credit is checked to the customer. This is just a scenario. I mean, there's many different scenarios we could walk through. So the situation is that we've got this little scenario here where there were 3 independent database transactions that occurred and a couple of really critical messages that can't be lost. Because if these messages don't get delivered, we have inconsistency in the system. Right? Which is a bad thing, because in the case of this order scenario, it's like you got orders that are stuck in the new state that never get into the approved state. And if you're the customer, you're going to be unhappy, right? And if you're the owners of the system, when you find out that you have this problem, you're going to really be unhappy because you need to figure out how you're going to fix this. So one question I want to have you think about just for a minute, and we'll come back to it. Is this does it matter if this is an asynchronous or synchronous exchange of messages? Okay, we'll come back to that, but think about it. So, at first, this kind of looks like you've got order on the one side of this scary bridge and customer on the other side of this scary bridge. And it's a scary bridge because there's all kinds of things that can go wrong getting messages from one side to the other. But I don't want to leave you with this. There are ways for handling this where you have the ability to make sure that every single message that has to be delivered gets delivered. Not all messages have to be delivered, but there are a category of messages that need to be delivered. So it's more like this, that you have a situation where you get a nice modern way of doing things, and messages are going to make it from one side to the other and back. It's going to work. But the way to approach this, right from the very beginning, and we were talking about this a little bit last night, was you don't say if things break, you say when things break. Right from the very beginning. When you're going through the design of your system, you're facing failure dead on. Eyes straight forward. So what will go wrong? And just in this little scenario, there's all kinds of things that will go wrong. The first one is that, say, when an order is created, that transaction has occurred, we're trying to send a message to customer, but we can't because the network's down. Or the message actually makes it to the customer side, but before customer can complete that transaction, it fails. Or the response back or the return message going back from customer after customer has reserved the credit, but before it can tell order, the network goes down again. Or the message made it back to order, and before order could complete that third transaction, it goes down, right? So all kinds of things are going to break. Not if, but when. When this happens, what's your system going to do about it? So back on the asynchronous or synchronous. When you look at, the point I want to make is when you look at this exchange, it's kind of a three-step process. It's 4 steps. The order was created, that's step 1. The request goes over to say, hey, order was created. That triggers some kind of reaction on the other side. Once that reaction is completed, there's some kind of message goes back. And the point I want to make here is that this is, no matter what technology you use to implement this, it's an asynchronous operation. Because what happens in order happens at time 1, what happens in customer happens at time 2, and what happens in order again is in time 3. Those are at different times. So you're fooling yourself if you think that doing like a RESTful synchronous call is going to help you in terms of breaking things. I really like how Gideon, right? You said that if you're doing HTTP REST, let's stop, right? Because there's so many things that will go wrong that when you have to deliver messages, they have to make it that you're not compensating for when you just do a simple implementation. And the scary thing is that you'll get this running, you'll get it into production, everything looks great, right? Everything's in production. And then you have a few failures, and you've dropped some messages, but you don't know. So time goes on, and maybe a few days after the failure, somebody comes up and says, hey, this data is inconsistent. My order's not, it's stuck in new. Why is it stuck in new? It should have been approved. Things like this. And then all of a sudden, it comes back to you guys saying, hey, we got this problem in our system. We lost some messages. I know you've delivered 1 million messages and you only dropped 10. Guess what? You're still a jerk because you dropped 10 messages. And you dropped 10 messages that you said you weren't going to drop, right? And then you look at the problem and you go, oh my gosh, we've got a really serious architectural issue here. To fix this is not going to be easy because we didn't face failure head on right from the very beginning and deal with it. So the situation is that for many people, we came from this really comfortable, great ACID world. We've been on ACID, right? Wonderful database transactions, everything works great. We start a transaction, we do all our changes, we commit it. Life's great, man. That's the monolith, right? Wonderful, well-oiled machine. Works great. You go into this distributed environment, and it's gone, right? You're talking about eventual consistency and transactions is happening. And that sequence of events that I showed you before with order and customer, imagine the monolith, that was probably a single transaction, right? But now you decompose that single transaction into multiple transactions. And there's some subtleties to this as well. There's things like, this analogy I want to use here is that you have an order transaction that occurred. And then you get into Kafka, which is this big, beautiful Airbus, right? and it's as safe as can be. You get an Airbus, and barring a mechanical problem that you don't leave the gate or weather or whatever, you're going to go from your origin to your destination, no problem. Airline travel is one of the safest ways to travel. But there's getting up those stairs, right? There's risk there. You could fall down, you could hurt yourself, and you're never going to make it on the plane. So the point is that there's these gaps between safe places. There's a safe place where you complete transactions. That's a safe place. There's a safe place where once you get a message into Kafka, Kafka is going to get it to the other side. But it's that gap that you've got to consider. Same thing on the other side. The message made it through Kafka to the other side, but now you need to pull the message into your application, into the consumer, and there's risk, periods of vulnerability is what I call it. So to address this, there's basically two approaches that people use, a push approach and a pull approach. And there's semantics to messaging. There's at most once, at least once, and exactly once. And I like to call it at most once, maybe once, right? Because at most once means most messages make it through, but some will not. And that's HTTP REST, for example, right? Some will not make it. At least once is once or more. So it's going to be that every message will make it through at least once, but some messages are going to be delivered more than once, which has consequences, right? You have to think about that. And exactly once is, I like to call essentially once. It was one of our CTOs, Victor Kling, he coined this term, I think, essentially once, meaning that exactly once is exceedingly difficult to do. And Confluent just came out with earlier, I think it was back in September, they came out with exactly once messaging in Kafka. And but they were very open about it because it was really super controversial when they said we're going to do exactly once. Everybody's going, oh no. And the way I look at exactly once is like trying to break the speed of light, right? It's not going to happen, not yet. So, but they were very clear about what they're doing and how they do it. And basically, it's essentially once, because what they're doing is they have once or more, but they're filtering out the dupes. They're deduplicating messages when they get to the other side. And somebody brought up a really good point when I was talking about this. They said they actually did us a favor by saying exactly once because they got us all thinking about messaging and the semantics of messaging. How many of you guys are familiar with the Simian Army at Netflix? Awesome. Anybody doing it? Dang. A little bit?
Somewhat.
Somewhat?
Yeah.
So, Simian Army, if anything, I'm a big fan of this. I've almost never seen anybody that says they're doing it besides Netflix. But the idea is that when you put something into production, there's a whole team with a bunch of really cool tools. They're going to go out and abuse your application. You can abuse your service. They're going to break it. They're going to do production outages in production to see if your service can stand up to it or not. And if anything, you should go away from here thinking that you work at Netflix. Because what it did, I think, at Netflix, and I know some folks that work there, is that it had a psychological effect on us as developers. Because imagine if you're a developer at Netflix and you go, oh, we're going to do a release. And then those chuckleheads on the Simian Army team are going to beat up our application, and they're going to look for vulnerabilities in our service. Oh man, let's go back and make sure that our service is going to be able to stand up to nodes going down, the network going down, the network's getting slow, all the things that will break, right? So it's forcing us as developers and architects to think about these things much more deeply, because if you're a Netflix, you know that these things are going to happen. I was in an airline once, and I was talking about this, and I said, I forget how it came around, but it came around, it's like, would you guys do this? Oh no, we could never do that in production. It's like, dudes, wait a minute. You're the airline. You guys have had legendary outages. Delta, United, Southwest have had outages where millions of passengers are impacted. And it's because they're not sufficiently hardening their systems. And they have this attitude, oh no, we'll wait until it happens in production for real, and then we'll figure out how to fix it. It's like, man, no, that's not the way to do it. So anyways, one of the points I'm trying to make here is that there's these non-transactional gaps that you have to account for. You have these comfort zones where there are transactions, like within a transaction on a database or within messaging through Kafka, but it's those gaps between doing a transaction and then maybe emitting an event and then putting it into Kafka to be delivered to some other side. You got to consider when it breaks, right at the worst possible moment, what are you going to do to make sure you don't lose messages? And this applies for things like just getting it into Kafka, right? So back to the two approaches, the push or pull. Either one's approach is great, but there are some mechanics to it. So in general, with a push approach, there's some kind of a log of messages that need to be delivered, is a typical approach. And there's some kind of retry, because you're trying to send messages from the producer to the consumer, and when messages don't get delivered, you got to have some kind of retry logic. So there needs to be some kind of persistence on the messages that haven't been delivered yet, and you have to have all this kind of plumbing in place. So that's fine. This is a common approach. And again, don't think you can get away with this with Kafka, because it's like you do a transaction, the transaction's done, you've committed it, and now you make a call to Kafka. You're in that period of vulnerability, right? When you can go right down at that point and the message doesn't get into Kafka and you've lost it and you're a jerk, right? So the pull approach is similar in that the producer is producing some kind of a log, but the consumer is the one that's actually pulling messages from that log. This is kind of the Kafka approach, the offset-driven pulling things. So the consumer is trying to keep up. The producer is just throwing messages into this list, and the consumer is trying to pull them as fast as it can to keep up. And same thing applies. This is a technique that can be used to move messages into Kafka and pull messages out of Kafka. So this gets into event sourcing and CQRS, because I was talking about log, right? And the more I look at event sourcing and CQRS, the more I like it because of things like this, that this log not only becomes handy for things like thinking about events when you're building a system in general, like from the domain-driven design approach, all kinds of advantages there, but now there's a big advantages for having events in a log in the system for things like messaging, push or pull approaches, right? It enables you to do these things much more easily. And this is kind of in general how it's set up. The commands come into the system. We heard about this yesterday. They go into an event log, but it also opens up other opportunities. Things like there's the log, the event sourcing on the one side, and then there's the query side. So they call it the write side and the read side. So the read side now has the ability to do things like having more than one place to put data. You could use your favorite database technology for queries, because now the data on the read side is optimized for queries. And it's not necessarily heavily normalized for handling both, the trade-off balance between optimizing a database for writes and for reads. Because now you have a database that's really optimized for queries, and the event log is a dead simple structure. You can slam data into that thing way faster than a database that's tuned for querying and for writing. You're always playing kind of a balancing game there. But it also opens up opportunities, things like you can have your favorite document database and favorite relational database here, right? Because if you've got messaging, at least once delivery, going between these things, and you're not going to lose any messages, then they're going to be eventually consistent, but you're always going to be able to get data from the event log into the query side. And then those guys will always be eventually consistent. So Pat Helen, we heard about him yesterday. If you've ever listened to Jonas Benair's talks, he quotes him quite often. There's three quotes I want to show here because they blew my mind when I first wrapped my head around it. The first one was, the truth is in the log, the database is a cache of a subset of the log. And the cache subset happens to be the latest value of each record and index value in the log. So it took me a little bit to kind of internalize it, because it was kind of like I was coming out of my acid haze, because when I realized, when I kind of wrapped my head around this, is that in the typical databases that we've been using forever, we're always saving like the current value, right? We're throwing away history. And here he's saying, well, underneath, the way these databases work all along is that they do logs. Logging is the truth. And it's just this veneer that we've been using. And it's like, that blew my mind. And then this next one, and he's got papers that back these up. So if you look for Pat Helen, you look for his papers, this is another famous one, accountants don't use erasers. And again, this came to, oh my gosh, we do CRUD, right? Create, read, update, delete. Every update, every delete, we're throwing away data. And not necessarily that that's a bad thing, but every time you update or delete, a data scientist cries, I think. You know, that you're getting rid of data that they probably would like to have. And data is becoming the new, you know, the new oil. Things like that. It's the new gold. Then this final one, and he wrote it in the era of SOA, service-oriented architectures, but I think it applies to microservices. And there's another paper for this one as well. Moving to microservices is like moving from Newton's universe to Einstein's universe. And his point was that in a monolith, it's a wonderful world, but it's Newton's world. Time is easy. Time is easy to understand. And in fact, one of the marvels of what relational databases do, or databases with transactions, what they do, is that from the perspective of every single transaction that occurs, all other transactions either happen before it or after it. This is all serialization, right? But if you think about it, every database transaction that occurs, all other transactions happen either before it or after it. It's a marvel of engineering. But that's Newton's well-ordered time universe. In Einstein's universe, time is all over the place. Time is relative. Our experience of time varies depending on many different factors. And the point that Pat Helen was trying to make is that when you move to eventually consistent distributed systems, time is different, right? What happens in, say, the order service happens at one time. What happens in the customer service, it might happen a few milliseconds later, but it could happen a few hours later, you know, if it's recovering from a failure, things like that. So event sourcing in CQRS, we've been implementing this for a while now in Akka. And it's actually called Akka Persistence and Akka Persistence Query, and it gets distributed using cluster sharding. So we use these boring names, but it's really, you know, the cool names these days is event sourcing and CQRS. These three things enable event sourcing and CQRS at the Akka level. It's pretty cool. It's actor-based, but from a developer perspective, setting this up is actually fairly straightforward. It's just some actor programming, nothing serious. And it works just like you would expect. A command comes into an actor. There's an actor per every active entity. So it's like, say we have a system of bank accounts, and a command comes in for a deposit to a bank account. It comes into a general actor who determines if that entity actor actually exists yet or not for that specific bank account. If the bank account actor doesn't exist, it's rehydrated with the data from the database. You know, it gets the current state of the bank account from the database. So now that actor exists in memory. The command goes through it. The command is validated, and if it's validated, an event is emitted, and an event is persisted in the data, in the event log, whatever that might be, Cassandra, relational, it doesn't matter. And then when the event is acknowledged, the entity updates its state. Like if it's a deposit, it adds the deposit amount to the aggregate, the entity, or if it's a withdrawal, it subtracts it. And then built into Akka is a pull approach. The right side is keeping up with the event log, and this is built into Akka to do this. It's fairly straightforward, but I think the Akka engineers decided on using the pull approach because it's a little bit easier to implement, and it's kind of a fairly straightforward way of keeping up. So what happens here is that the events could be going, say the read side goes down for some reason. Maybe it's a relational database and it goes down. The the service itself can keep running, can keep taking events. And when that database comes back up, then it just catches up, right? It just comes up. Its offset, say, is way behind, so it's just using its offset to try and keep up, get to the point of the latest log record. And once it catches up, now it's in sync again. But there's kind of this very straightforward way of not losing any messages and always keeping up. So using Akka for event sourcing and CQRS, people are building services using Akka and Akka HTTP, or Akka and Play, or Laga, like we heard yesterday. And what's cool is that when you're building services this way, you're building a service that's clusterable, which means you have the ability to have resilience by having more nodes than a single node, a single point of failure, and also scale. You can scale out. If you need more capacity, you've got the ability for capacity. So the way it kind of looks is that you have the nice thing about a microservice system is that there's no single point of failure. If say an individual microservice goes down, as I was talking about earlier, the system itself is still up. We take it a little bit step further. If you have, it's like clusters within clusters. You have a cluster of microservices, but some of those microservices could be clusters themselves. And if you take a hit and one of those nodes in the cluster, the microservice itself is still up. It gives you another kind of level of resiliency and scale. But that's not all. There's some other things that people are doing, I think, that are pretty interesting with systems that are architected like this, using event logs in particular. This one I think is really interesting, and I'm hearing about this more and more. In fact, there was a really good talk at Devox by Ben, what's his name? He's from Confluent. No, not he. Anyways, they were talking about Kafka, and one of the things that he brought up was what I want to talk about here. So the idea is that if you have reliable messaging, at least once messaging, worked out messaging, where you have an architecture where you're not going to lose messages, you have things like this. And the idea here is that, say you have customer is a service. So every time a customer changes, customer just emits an event, it broadcasts an event, doesn't care who gets it. It just, it's publishing an event, says, customer updated or something, right? Say order and shipping are interested in those events. They hear about this. Now, what this means is that order and shipping could have their own view of customer that they store in their own schema, right? So the idea here is that in order to do an order, you need customer information, right? Orders and customers go together. So one approach is that the order service, every time it needs customer information, it does a get from the customer service. This approach is where order has its own view of customer. So it's a form of optimization and a form of resiliency. But now it's able to go straight to its own database, its own schema, and retrieve customer information in a view that's sufficient for order. It no longer has to reach over the network. And you've eliminated you put a bulkhead between those two services. You don't have a possibility of cascading failure. Because if customer goes down, an order has to talk to customer to do orders. That customer goes down, it pulls order down, right? If you do it this way, you've got a nice bulkhead between the two, where customer could go down, but order can keep going, right? Because it's got its own view of customers, and it can do its thing. Shipping can do the same thing. Shipping could have its own view of customer as well. The idea is that you've got this reliable messaging, and you're eliminating the need for services to reach out to each other all the time. And think about it. Customer, I think, is a really good example, because how often do customers change? Very, very infrequently, right? But how often do you need to retrieve customer information? Very, very often, right? So that, again, the choice is you either have to reach across the network from order, and this could be a RESTful GET, right? When you want to retrieve customer information, but you're vulnerable there. If customer goes down, it could pull down order. Order can't do its work. So I think this is kind of an interesting feature, and I'm seeing this being pushed and implemented more and more. So, as I mentioned earlier, part of the challenge is it's not so hard in many cases to start to break apart your code, but in many organizations it's hard to break apart your data. So I wanted to kind of throw out, I'm just throwing this out, but maybe an approach. So the first thing I wanted to kind of throw out is that in order to do this reliable messaging, either push or pull, whichever approach you use, you need that log of messages that need to be delivered. So maybe in your existing database, you start to implement these simple log tables, right? So they're part of the transaction. You still have atomic transactions occurring. You still got tight coupling because if multiple microservices are using the same tables, they've got coupling and things like that. But you're starting to nudge things a little bit in the direction of giving you the ability to do at least once delivery of messages, things like that. And maybe you start to introduce more and more of these logs. But then maybe some of the services, you start to detach the log and put it into some other database. That might be a big one because depending on the organization you're in, setting up a separate database can be really, really hard. Other places, like, no problem. And then maybe, here though, the database is still the master. This log is still kind of secondary, right? But the next step is to make the log the master, and then maybe replicate back into to the database. So it's a kind of a gradual way to kind of pull away from the database. And then the final thing is you can cut the cord altogether, right? So you kind of weaned yourself from the database, maybe slowly in a few incremental steps to the point where you get a fully independent microservice that owns its own schema, owns its own data, and the only way to the data is through the APIs of the service itself. And I just wanted to wrap up with, we're here, right? We're at the end of 2017, and this is one projection on the increase in the amount of data that we're going to be faced with in the not too distant future. This projection, I think, is a tenfold increase by 2025. And I think this is kind of conservative. I think in many cases we're going to see more data. And more data to me means more database technologies are going to run out of gas, right? You're going to run into those ceilings where the databases can't go any faster. Or the approaches that we've been using with these nice, comfortable transactions that we do in our databases are we're going to run into those points of contention where we're not going to be able to push them any further. We're just not going to be able to handle the tsunami of data that's coming at us. And it all comes down to, we're obsessed at Lightbend with, this isn't just something that we're saying, this is something that we do. This whole reactive, the characteristics of reactive, resiliency and elasticity are paramount with us. And for example, talk to Renato about logom. Logom, all these things I've been talking about, the pull, handling those non-transactional gaps, are all built into logom. It's just there. The developers can't screw it up. That's part of the opinionated way of the way logom works. All those non-transactional gaps are covered, right? And the thing that drove me nuts, though, is when I first came to Lightbend and I first started learning about logom, it's like, where is this documented? This is like the most important feature of logom. They're not saying anything about it. It's like, we were talking about it earlier. It's like, man, this is important stuff, and we're focusing on the code. And it's like, okay, yeah, the code's interesting and it's important, but maybe you need to know a little bit about the mechanics that's actually in there and why you're coding in this way, in this opinionated way. But we cover these things. Akka is the same way. It's Akka, we just came out with multi-data center, and there's all kinds of talk in there and considerations for resiliency and distribution. It's just part of the nature of the way we do things. So that's it. Appreciate the time. Any questions?
Thanks for the talk. I think this makes a lot of sense. But one thing that changes is that where we used to have one single code, we now have to write to the event log and pull from that log. So we're going to have increased latency. So I'm just wondering if you have any advice or tips to reduce that latency.
Yeah, the question's really good about latency, right? The eventual consistency. And I think it's one of those other things that you really have to think about from the architectural level that because it's things like, like the classic was you have an orders processing system and you don't want to fulfill an order when you're out of inventory, right? And so it's the situation of you can't have eventual consistency because you have to know when that last book was sold, right? But the realization is that no, the business wants to take orders. They don't care if they're out of the book for a few days. They'll fulfill that order. But don't tell the customer, I can't take your order because we're out of books, right? So it's that kind of change in mentality of the reality. It's like in order to do a distributed system, the physics, the speed of light, things like that just dictate. And we were talking about this last night, that if you talk to the business, they don't care about some of the things that we've been agonizing over at a technology level. Things like not fulfilling orders, not doing a withdrawal when that last euro went out of your account, things like that. Because there's a difference between, say, an overdraft where the customer knows they're overdrafting, or an overdraft because of some kind of a hiccup in the system. There's things like that. And so if it's due to eventual consistency, that's one thing. But I think it's kind of us letting go of some of these things that we've cherished so deeply for so long, and kind of going back to the business and talking to them and saying, well, do we really have to do things this way? And in many cases, I think they're going to say, well, I don't know why you guys were so, all caught up in this, because we don't care. If the inventory's out, we know we got a supply chain. The supply chain is going to feed that order, that item that's out, and we'll get it back in a few days. So instead of getting the delivery tomorrow, some customers get it in 2 days, or next week or something. But I think in many cases it's rethinking the system that, and it's read some of those Pat Helen papers. I think it really sheds some light on things. It really makes you rethink, data on the inside, data versus data on the outside. Accountants don't use erasers. All these things that I know. I think there's a different way of thinking about architecting a system that, to me, feels actually a little bit more natural now than it did when we had the comfortable, crud, atomic, world that we've been living in for so long.